Hello everyone, myself Impan. I am G studying in Sri Venkateshwara College of Engineering. Today I am going to talk about programming techniques for turning machines, extensions to the basic turning machines. Introduction to turning machines. Turning machines are the abstract computational models that define the limits of what you can be computed. They consist of an infinite tape, a head that reads and writes symbols, and a set of states. Understanding turning machines is essential for grasping the fundamentals of computation theory. Components of turning machines. A turning machine includes a tape divided into cells that can hold symbols. The machine has a head that moves left or right to read and write symbols on the tape. A finite set of states governs the behavior of the machine based on the current symbol read. Basic operations of turning machines. The turning machines operates by reading a symbol from the tape and trans, trans, transitioning to a new state. Depending on the state and the symbol, it may write a new symbol and move the head. This process continues until the machine reaches a designated halting state. Programming techniques overview. Programming a turning machine involves defining the transition functions systematically. Techniques vary from simple state machine design to more complex algorithms. Effective programming can simplify the representations of complex computations. Transition functions. Transition functions map the current state and symbol to a new state symbol and a head movement. They can be represented in tabular form for clarity and easy of understanding. A well-defined transition function is crucial for the machine's intended operations. Encoding input and output. Inputs can be encoded on the tape using a specific alphabet of symbols. The output is also represented on the tape, which can be read after the machine halts. Proper encoding ensures that the machine can process various types of data effectively. Multi-tape turning machines. Multi-tape turning machines have more than one tape, allowing for parallel processing of information. With multiple heads, these machines can read and write on different tapes simultaneously. This extension significantly increases computational efficiency and complexity. Non-deterministic turning machines. Non-deterministic turning machines can have multiple possible transitions for a given state and symbol. They explore different computational paths simultaneously, providing a powerful abstractions. This model is useful for understanding complexity classes such as NP. Universal turning machines. A universal turning machines can simulate any other turning machines given its descriptions and input. It represents a significant theoretical advancement in computation, showcasing Turing's ideas. This concept leads to the foundation of modern computer architecture and programming. Recursive functions and turning machines. Recursive functions can be computed by turning machines, establishing a connection between the two fields. This relationship is fundamental in proving the church turning thesis. Understanding recursion aids in designing algorithms that turning machines can implement. Complexity and time complexity. Time complexity measures how the computation time grows with the input size on turning machines. Analyzing complexity helps in evaluating the efficiency of algorithms implemented on turning machines. Different classes of time complexity provide insights into feasible computation limits. Space complexity. Space complexity accesses the amount of tape used by the turning machines during computations. Understanding the space requirements is crucial for optimizing the design of algorithms. Like time complexity, identifying space complexity classes helps categorize computational problems. Simulating algorithms on turning machines. Many classical algorithms can be implemented directly on Turing machines. The process involves translating high-level algorithmic steps into state transitions. This simulation reinforces the versatility of Turing machines in algorithms, representation, error detection and correction. Turing machines can be designed to include mechanisms for error detection during computation. Implementing error correction algorithms ensures reliability in outputs. Understanding these techniques is vital for particular computational application. Partial applications of Turing machines. Turing machines serve as theoretical models for various computational applications. They are instrumental in the design of programming language and compilers. Additionally, Turing machines contribute to advancements in artificial intelligence and machine learning. Limitations of Turing machines. Despite their power, Turing machines cannot solve every computational problem. Problems such as the halting problem demonstrate inherent limitations in computation. Recognizing these limitations is crucial for fields such as computer science and mathematics. Relationship with other models of computation. Turing machines relate closely to other computational models like finite automata and push-down automata. Understanding these relationships enhances the comprehensions of computational theory. They provide various representatives on how computation can be structured and analyzed. Conclusion of Turing machines theory. Turing machines theory lays the foundation for modern computer science and computation. Its principles guide the design of algorithms, programming language, and hardware architecture. Continuing to explore Turing machines extension fosters innovations in computational techniques. Further directions in Turing machines research. Further research may explore new extensions or applications of Turing machines in quantum computing. Innovative programming techniques can emerge from evolving landscape of computational theory. Understanding Turing machines remains crucial as technological advance and new challenges arise. Thank you everyone.